Today's lesson is on 9.2 factors affecting dissolving and solubility. So, good evening, everyone. Today we are looking at 9.2 factors affecting dissolving and solubility. So, one thing to make note that anytime we have an aqueous solution, we are dissolving in water. So what we're going to be looking at today is what are the factors that cause this kind of solubility or this kind of dissolving to actually occur. Understand that there is a difference between dissolving and solubility. Dissolving relates strictly to the actual act of breaking down of the particles. Solubility looks at how much can possibly dissolve in a reaction. So the dissolving is really just the physical act. The solubility is more the numeric values of the way something is soluble in some kind of a solvent. Okay. So the rate of dissolving, very important property of solutions. We talked about solubility way back in 1.1 when we looked at some of the physical and chemical properties, and it is considered a physical property, but a quantitative physical property. So there are three factors that affect the rate of dissolving. Okay, so we've got temperature, agitation, particle size. So best way to kind of, to describe that is the idea of mixing sugar into coffee. Okay, so we think about coffee and we think about coffees typically served hot. So if the temperature is high, meaning a warm temperature, hot temperature, the ability to dissolve more will be there. So let's say you're trying to sweeten a hot coffee as opposed to a cold coffee, like an iced coffee. A hot coffee will be able to dissolve more sugar than an iced coffee because temperature directly affects the way something dissolves. So, temperature affects dissolving for most solid solutes. The rate of dissolving is greater at high temperatures. Okay, so if I want to dissolve more, I want to make sure that my temperatures are high. So one of the reasons for that, well, at high temperatures, the solvent molecules, so imagine that the liquid aspect of coffee, the kinetic energy is very high. And so what happens is they will collide with the particles of that sugar more frequently, right? Because the warmer something is, the more kinetic energy is storing, because that movement, right, that vibrations, and those vibrations of the particles increase as the temperature increases. Now, agitation affects dissolving. Think about the first thing you do the minute you pour, or if you've seen someone pour a spoonful of sugar into a cup of coffee, and the first thing they're going to do is to stir it. So stirring it is that agitation, that mixing, maybe shaking the container, that will increase the rate of dissolving. Okay, it'll increase the rate of dissolving. Why? Because the agitation will bring fresh solvent into contact with the undissolved solute, right? So the minute you start stirring it, all of a sudden now you are causing particles of that sugar to come into contact with more aspects of the heated solvent. And particle size affects dissolving. So decrease the size of the particles increases the rate of dissolving. So think about sugar, and typically sugar comes in little granules. Okay, I remember as a kid, and I don't know if they still have them. but sugar cubes, right? So I remember people having these sugar cubes, and people would pop these couple of sugar cubes into, let's say, their cup of coffee or into their tea, and then stir it. Understand that the rate of dissolving will be faster if the particles were a lot smaller. Why? Because what happens is the smaller the pieces, the greater the surface area that is coming into contact with the liquid. So imagine these little granules, right? And the surface area of those little granules, and how all those granules have the ability to kind of get exposed to the liquid solvent that is the cup of coffee. But if you throw in a sugar cube and let it dissolve as is, understand that the sugar cube, the liquid, right? So that coffee is going to try to slowly dissolve and slowly try to eat away at that cube. But understand that this cube is three-dimensional. So the particles that are held within the sugar cube will not be coming into contact immediately with the solvent, with the coffee, to cause that dissolving. So the best bet is, if you were to use a sugar cube, was to actually try to crush it with a spoon or your fingers, let's say, before you're putting it in, if you want to get a quicker result for your dissolving. So reasons why a solute may or may not dissolve in a solvent are related to the forces of attraction between the solute and the solvent particles. So when the forces of attraction between the different particles in a mixture are stronger than the forces of attraction between particles in a mixture, a solution forms. Okay, so all of a sudden it's the idea that, well, we know that water molecules have an attraction to other water molecules. We know that salt has an attraction within its respective ions. And so what happens is, this force of attraction, this is that attraction that's holding either the salt or the ions together, or what's holding the solvent together. And so what happens is we need to overcome that strength, and all that is going to require energy. And that's where we come across what is referred to as the process of dissolving at the molecular level. And there's 3 steps to this process. We talked about the first 2, the idea of breaking apart the particles that are being held together within a molecule, or between molecules or between ions. Okay, so let's look at step number 1. So the forces between the particles in a solid must be broken. So think about that NaCl. Right, that we've got to break apart. There's an attraction here between the positively charged sodium and the negatively charged chlorine. So we've got to overcome that attraction. So in an ionic solid, just like we've got up here with the NaCl, the forces that are holding the ions together must be broken. Okay, if we were looking at a molecule, we would have to break apart the molecules that are holding together, and all that is going to require energy. Okay, so to break the attraction between an ionic bond or between the forces of molecules, right? And so the force of molecules, talk about covalent attractions, right? Hydrogen bonds, they need to be broken, and they all require energy. The second thing that requires energy is the intermolecular forces between the particles of that liquid. So I drew it before with the water molecule, right? So we've got one water molecule attracted to another water molecule, attracted to another water molecule, and so forth and so forth. Now, this attraction, that needs to be overcome. So we need to break this attraction, right, between the molecules, to allow for each molecule of water to surround each ion of, let's say, whatever it is dissolving, or around each molecule of whatever it's dissolving. And to do that, it also requires energy. And the last thing is that there is an attraction between the particles of a solid and the particles of a liquid. And this step will give off energy. Now, let's redraw that NaCl. Let me change the color here. So we've got the NaCl, and we break apart the NaCl and the So we break apart the salt. And so what happens is with the water molecules, right? Think about polarity that we talked about back in chapter 3. Remember that water, the oxygen is slightly negative. So because the oxygen is slightly negative, the water molecules now will no longer have an attraction to other water molecules, but they are going to have an attraction with the oxygen part of water will have an attraction to one of the ions, and the Na, as in this example, right? Because as we said before, or moments ago, that oxygen in a water molecule is slightly negative and slightly positive. So we use the lowercase delta negative and the lowercase delta positive to demonstrate what's slightly positive and slightly negative on on a covalent compound that contains polarities, and that polarity implies having slightly positive and slightly negative ends. Now, we have chlorine on the other hand. Chlorine being negatively charged, it will have, let me try to keep the colors consistent. It will have the hydrogen part of water surrounding it, because in a water molecule, right, as we said, the hydrogens are slightly positive. So the slightly positive hydrogens are going to surround the Cl negatives. So if we have what's referred to as a saturated or even an unsaturated solution, right? It means that we are going to maximize the amount of solute that can dissolve. So maximize the amount of, let's say, salt in this example that will dissolve, or if it's unsaturated, meaning that there's room to apply more salt. And so each salt molecule will break apart and have, all these water molecules surround it. And that's the reason why when something dissolves and you don't see it, it's because it's technically hiding behind molecules of whatever that solvent happens to be, and we've shrunk it down to something so tiny that, well, it's surrounded by whatever the solvent is, and hence the reason why we can't see something that is dissolved in that particular solution. Okay. So polar and nonpolar substances. So the idea that like dissolves like. So polar solutes will dissolve in a polar solvent, and a nonpolar solute will dissolve in a nonpolar solvent. So the idea that like dissolves like, it means that I need to have polarities. They need to be polar, so or both nonpolar. Okay, you cannot have a polar substance dissolve in a nonpolar. Prime example of something like that: oil and water. Right? Oil is nonpolar, water is polar. Hence the reason why they will not mix with one another. So solubility and intermolecular forces, we just talked a little bit about this moments ago, but just to kind of recap and bring up a couple of key points here to this concept that I just mentioned. The term dipole, and the dipole, so the di meaning two poles. So the two poles are a slightly positive and slightly negative end. Okay, and understand that pretty much that the polarity always moves from, let's change the color, from a positive to the negative end. And so actually I shouldn't have done that. Okay, so the arrow represents the direction of where the slightly negative part is, and this positive here, this looks like a positive symbol, right? That you kind of create with the arrow, shows where the slightly negative ends will be. So dipole attractions. This is what holds water together. Okay, so what holds water together are these dipole attractions. So if the force is greater between two different dipoles than between the dipoles of the same molecules, then the solute will actually, in fact, dissolve in the solvent. Okay, because let's face it, if the attraction between the molecules of a solvent is very strong, remember that it requires energy for it to break them apart. So not necessarily will that always, in fact, happen. Okay. So ion dipole attractions, perfect example that we just talked about moments ago. Here is the sodium chloride. Okay, so the salt example. So here we have the Na of NaCl, right? The positive, and here we have the Cl negative. And notice what part of the water molecule surrounds each molecule. So what happens is here's our granule of salt, and the salt gets attacked. So the salt gets attacked by the water molecules, breaking apart the attraction that holds the ions together and cause the dissolving to actually take place. So here it is, just kind of another diagram. But to understand that when we have the dissolving of an ion, we are creating an electrolytic solution. So they contain ions that will actually conduct electricity. Okay, so this is also referred to as the hydration of ions, and it occurs when water molecules completely surround the ions. And as a result, creating these charges that can allow for the conductivity of electricity. Not all ionic compounds are soluble in water because the force of attraction within the ion compounds are too strong to be broken apart by water molecules. Okay, so here's an example. Silver chloride, if you look at it, it is ionic. However, the attraction between these two ions is very strong, and because it is very strong, it will not dissolve in water. So understand that not always do you have dissolving occurring with ionic compounds. Most of the times, yes, but there's the occasional time where it is no. Predicting solubility, not really all that cut and dry. We're going to try to simplify it in this unit as much as possible, but a few key things to be aware. When predicting solubility, use differences in electronegativities to determine the ionic nature of a compound to help predict solubility. So let's take, for example, we have methane. Okay, CH4. Understand that the slightly negative aspect here is carbon, but carbon is surrounded by a bunch of hydrogens that are all slightly positive. So for something to get in there, right? So we need something slightly positive or even positive to be attracted to this central atom. However, how do you get something that is positively charged in here when you have a molecule surrounded by a bunch of slightly positive ends? So what's going to happen is they're going to repel anything from trying to come in. Hence the reason why, even though we've got this slightly positive, slightly negative, if you look at the change in electronegativity, you will notice that that change in electronegativity is less than 0.5. Go back to chapter 3 where we talk about electronegativity and the polarities. So if something is less than 0.5, for the most part, it is considered non-polar. Okay, even though it has these slightly positive, slightly negative ends. However, the slightly positive, slightly negative, right? We always go from the positive to the negative, positive to the negative, positive to the negative, positive to the negative. I think I did a diagram like this back in class, back in late February. But notice how the negative aspect of this polarity is in the center. So to reach that, it's going to be difficult with all the slightly positive attraction towards the outside. Hence the reason why this is considered also non-polar. Now, if elements are polar or ionic, then the compound will probably dissolve in water. Now, if the element is non-polar, then the compound will probably not dissolve in water. So understand that for the most part, most of the times, yes, ionic and polar means that they will dissolve in water most of the times. Okay, and if it's nonpolar, it will probably not dissolve in water. But understand that in science, there's always the occasional exception to the rule. But for the most part, as an umbrella understanding here, we're going to look at it as if it's polar or ionic, it will dissolve in water. If it's nonpolar, it will not dissolve in water. So solubility of covalent compounds, understand that nonpolar covalent compounds do not have dipole charges, right? Because as I showed moments ago here, there's no dipole charge in this example, hence the reason why it's nonpolar. Now, there are some exceptions to the rule. A hint, if you look at this one, carbon-hydrogen. Carbon-hydrogen, this is a hydrocarbon. Hydrocarbon. Okay, so hydrocarbons typically are nonpolar. There's a whole science to it. It's organic chemistry dealing with carbon-hydrogen compound molecules. Now, there are some exceptions to the rule, and we're talking about pretty much hydrocarbons that contain oxygen ends. Okay, so those bio students, the OL ending means alcohol or OH. Functional groups, the OH is very polar. Okay, so because something like methanol is pretty much a derivative of methane. Okay, so instead of H's on all four of the bonds around carbon, one of them will actually contain the OH, and this OH part is what will be the polar ends. So these polar ends here that we see, okay, are what allow for them to actually dissolve in water, because they do come into they can come into contact with water to allow for dissolving to actually take place. Okay, here's just a molecule of a sugar, and notice the water molecules that and where they can actually surround the molecule of sugar. Okay, so even though they have a bunch of nonpolar ends, because they actually do have these polar ends, okay, look at all these polar ends. Lots of locations for water to actually be attracted to, hence the reason why sugar will actually dissolve in water. So if a compound possesses both polar and nonpolar components, it may dissolve in both types of solvents. It may dissolve in both nonpolar and polar. So here's an example of acetic acid. Okay, so here we have the nonpolar end, and here we have the polar end. Okay, because it's pretty much a half and half molecule. This half molecule is what's going to allow for dissolving to actually occur in something that is polar. However, if we were to dissolve this in a nonpolar solvent, this is the part here that will allow for that non-polarity to actually take place. So here we have an insoluble covalent compound. This is the methane that I was talking to you about moments ago that I had drawn. Okay. So here are just some examples of polar and nonpolar substances. No point to memorizing any of that. Just if you look at a substance, being able to find the change in electronegativity between the bonds is good enough to allow you to find out if something is possibly polar or nonpolar. So if you look at it again here, these two are nonpolar because look at the polarities. Polarities moving in a direction. So this center is the one that's slightly positive, and all this to the outside is slightly negative. So for something that is negative to be attracted within here, it would be tough because surrounding the actual central atom is a bunch of negatives. Same thing will apply with this example here of BF3. Anything that is diatomic, no point to checking the change in electronegativity, because the change in electronegativity is the electronegativity of one atom subtracted by the electronegativity of a second atom. And if they're the same atoms that they're bonded together, it will be 0. Okay, and simply with these ones, again, no need to even memorize these ones, just even drawing them and finding out what the bond will be, and their change in electronegativity to identify if something is considered polar or non-polar. Okay, so now all that we talked about was looking at the ability for something to dissolve. So the actual physical act of dissolving. Okay, now we're going to be looking at the factors affecting solubility. Okay, so notice that these factors are similar to the factors of dissolving, but they are not the same. Okay, so not to be confused. So the factors that affect solubility, the molecule size, so how big is the molecule, what pressure is being exerted by the solution, and lastly, the temperature. Okay, so this is more for the mathematical aspect of dissolving. Okay, so we're looking at the quantitative results of the actual dissolving. Okay, so molecule sizes, pretty much the smaller the molecule, the more soluble it is. Okay, so take for example here. Notice here we methanol, the smallest alcohol we can have here. Now add another carbon in that, so extend the chain of carbons. It's getting longer. It's getting longer. It's getting longer. It's getting very longer. But notice now how that dissolving changes. So we're talking about infinitely soluble, meaning there's so much that can be soluble in water. However, as we get larger, as the molecule itself creates a longer and longer hydrocarbon chain, right? This is a hydrocarbon chain, carbon and hydrogens. Remember what we talked about between carbons and hydrogens, how they are nonpolar. So the longer the nonpolar end becomes, the less soluble the substance is in water. Pressure. Pressure usually affects gases. Okay, so for solids and liquids, they will not affect. But when we're dealing with gases, the pressure plays a very big role in solubility, right? So the greater the pressure, the more we can dissolve. Hence the reason why a pop bottle is under pressure, because we are dissolving so much carbon dioxide within, right? All that carbonic acid that's going to decompose to form the carbon dioxide once we open the cap or open the can of pop to release, right? So for that to be effective as a drink, right? When people buy things that are carbonated, they want that fizziness, and in order to have that fizziness, we need to increase that pressure so we can dissolve more gas within the actual solution. And finally, temperature. Temperature plays a very big role in the solubility of solids. So as temperature increases, solubility is also going to increase. Okay, and that's because the temperature, you increase the kinetic energy, therefore you're giving the molecules more energy to actually cause the dissolving. In terms of liquids, if you mix liquids together, doesn't matter what the temperature is, they are unaffected by changes in temperature. So you put together two liquids that are very miscible. Remember we talked about liquids are miscible with one another, so they don't really dissolve in one another. It's kind of hard to tell which is a solute solvent. Okay, so ethanol, okay, plus water. Okay, so it doesn't really matter if we increase the temperature of the water, increase the temperature of the ethanol, it's going to mix the same way regardless of their temperature. And lastly, gases. Gases, the solubility of gases, in fact, will decrease as temperature increases. Okay, and that's because gases generally will lose energy as they dissolve. Okay, so therefore an increase in the temperature gives the gas more energy and therefore decreases their solubility. Okay, so all of a sudden it's like the gases already have their own kinetic motion. The minute you introduce something else into it, it will slow down that motion, okay, until it reaches a specific temperature. And so as a result, the minute that gas gets introduced to that change, it will lose energy in terms of their dissolving. So temperature and solubility of solids. Increase the temperature usually increases the solubility of a solid in liquids. And this is according to the second law of thermodynamics, where increased temperature means a greater average velocity for the particles. As I increase the temperature, okay, so think about an ice cube. And the particles of an ice cube, they slightly vibrate. But the minute I add heat to that ice cube, and it eventually melts, the reason why it melts is because the particles start to vibrate so quick that eventually they start to break apart some of the bonds that are holding the solid aspect together to allow for that flow between molecules of water. As I increase the temperature on that liquid, eventually it will evaporate into a gas, right? Because the particles are moving so quickly. Okay, so this allows them to move from one position to another more easily. The greater freedom of movement allows the system to change its state more easily. Okay, we're talking about saturated versus unsaturated solutions last class. So what we have here is some kind of a solute that we are dissolving. So if we look at the dissolving that's occurring here, we've got 100 grams that we've put in, and right now only 5 grams has dissolved, right, at 25 degrees Celsius. So right now it is considered unsaturated because we have room to dissolve more. So eventually we've maxed out the amount of what we can dissolve. So right now we've got a 9-gram precipitate at 25 degrees Celsius. So right now the solution is saturated, meaning it has dissolved the maximum amount of solute in that solution. Now, that's it. At that temperature, I cannot dissolve anymore. So this reaches what's referred to as a dynamic equilibrium, because what happens is a molecule will solidify into the precipitate and to allow for another particle to dissolve. Okay, so it kind of goes like back and forth between new and old particles. Now, what happens here is I'm adding heat. Okay, so I'm adding heat. And so I'm all of a sudden increasing the temperature from 25 degrees Celsius to 50 degrees Celsius. Because remember what we said earlier, if we increase the temperature, we are allowing to dissolve more solids. So the remaining 9 grams of precipitate has dissolved with the higher temperature. So what happens now is I'm going to cool this off. Okay, so if I cool this off, I bring it down to 25 degrees Celsius, we would assume, oh, wait a second, doesn't it won't the precipitate form? Well, the precipitate won't form right away until it gets disturbed. So there's got to be some kind of disturbance to cause the dissolved particles to start to crystallize again. Okay, so in this case, because the precipitate hasn't come back, we've lowered the temperature back. All of a sudden, this is what's referred to as a supersaturated solution. Why? Because at 25 degrees Celsius, I can only dissolve 9 grams. How do I have 100 grams dissolved instead? And that's because I've increased the temperature. I've caused all the 100 grams to dissolve. I lower the temperature slowly back to the 25 degrees Celsius. At that point, that is when we have a supersaturated solution. Eventually, throw a stick in there, throw a piece of thread in there, and eventually, around that stick, the ions are going to realize, hey, wait a second, we are only allowed to dissolve up to a saturated point. So eventually, whatever has become part of that supersaturate, those ions, that 9 grams of precipitate, will start to crystallize in solution. And this is pretty much how rock candy, right? So if you've ever had rock candy treats, okay, if you've ever seen people making crystals, I do have a video of a student teacher. If you look it up, I think if you look up supersaturated solutions on my channel, you'll see a great demonstration that he once did in class with regards to supersaturation. Pretty cool, actually. You don't even have to look for the one on my channel. Just look up supersaturated or forming crystals on other on YouTube, and you'll find a whole bunch of really cool stuff out there. Okay, so solubility curve. So solutes normally dissolve in a particular solvent up to a specific limit. So the maximum mass of solute which dissolves in 100 grams of a given solvent is called the solubility of the solute in that solvent. So what we're going to look at is what is referred to as a solubility curve. So here is a solubility curve of various substances. And if you look at these various substances, it will show you exactly how temperature affects their solubility. And if you notice here, right, sodium nitrate, potassium nitrate have rather steep solubility curves, meaning that as temperature increases, their solubility becomes great. However, look at something like sodium chloride. Its solubility doesn't really pretty much plateaus. It doesn't quite increase in terms of as some of the other ions. And then here's another one where in fact it actually lowers as the temperature increases and eventually plateaus. Okay, so one of the things that I'm going to want from you in this chapter is to be able to read a solubility curve and try to figure out how much can dissolve within a specific temperature. Okay, so here's a couple of sample problems. So if we had potassium chlorate solution is cooled from 80 degrees Celsius, so 80 degrees Celsius to 50 degrees Celsius. What mass of precipitate out of the solution? And then in question number 2, a saturated solution of potassium nitrate is cooled from 50 degrees Celsius to 10 degrees Celsius. How many grams of this salt will precipitate out at 240 grams? Okay, so here are the answers again. With regards to these are going to be estimated values, but it's important that you, when you're reading, you do the best you can with regards to making that assumption. Okay, don't rush to make your assumption. Understand that between any 2 points, right? So between any 2 points, so let's say between 70 degrees and 80 degrees here. Okay, understand. Try to figure out ballpark-wise where is the middle. Okay, where is the midpoint? And then from there, right, because that midpoint is going to represent your 0.5. And then from those midpoints, create new midpoints. Okay, create new midpoints to give you a ballpark of where 2 might lie, or where the 0.3 might lie, or where the 0.7 might lie, or where the 0.8 might lie. Because what happens is students oftentimes are like, the point is between the 70 and the 80 here. That looks like 70.5, or should I say 75? Actually, sorry, not 0.5, 75. Okay, and they're quickly rushing to it. So take the time, be as accurate, be as precise as possible when you are deciphering between points that don't lie exactly at the whole points of a graph. Okay, and the last point that we're going to look at, dissociation. Dissociation is really what does the dissolving actually what does it look like in terms of an actual equation? Okay, so here's an example of the dissolving or the dissociation of sodium chloride. So here's sodium chloride in a salt. If I dissolve it in water, it will break apart into its respective ions. So it's going to form an aqueous solution. So another way of writing this is NaClAq. Or another way of writing NaClAq is as such. Look at the cation. The cation is Na. The anion is Cl. What are their charges? So the Na on the periodic table is positively charged. Chlorine is negatively charged. And don't forget the little AQs. Understand that in this unit, because we are looking at solubility, these states are going to be now important to include, and we'll see a little more of that in chapter 10, I believe. So when ionic compounds dissolve to produce ions, the process is typically called dissociation. So dissociation of an ionic compound occurs when water molecules pull apart the ionic crystals. So we've got that Na attracted to that Cl negative. So what we're doing is we're pulling them apart. Okay, that's what's caused the that dissolving. So when water molecules surround the Na aspect or the Na ion or the Cl ion, this is what's referred to as a hydration of the ionic substance. Okay, and lastly here, some sample problems. It's going to ask you to write dissociation equations for the following compounds. Okay, so notice for the most part, they're most of them are AQ. I could have included that as AQ if I wanted to, but what we're relating it to is if it's not as an AQ, it means I'm dissolving it in water. And what's it going to look like? Well, it's going to look as such. So our our NH4 here is the cation, the Cl is the anion. Okay, in this case, Pb plus 2 and this sulfate. Ones to be aware of is that even with these ionization equations or dissociation equations or these aqueous equations, they still need to be balanced. So take, for example, this one here. So let's break this one down. Na2SO4. Okay, so this is AQ or S, whatever it is. It doesn't really matter. So we've got the Na, okay, and it's positively charged, AQ, plus SO4, AQ. So all I'm doing right now is identifying what's my cation and what's my anion in my ionic compound. Now, then I got to look at how many NAs are there in this equation. In this compound, and there are 2 of them. So that 2, I don't put that 2 as a subscript. I put that 2 in front. So when I'm balancing, there's no such thing as diatomics. Okay, there's no such thing as diatomics. Everything is written as the ion, how they actually exist in nature. Okay, if you look at this example here, right, we've got a calcium, we've got a phosphate, okay, but now we want to look at how many calciums do we have. We've got 3 of them. How many phosphates do we have? We have 2 of them, and there would be our balanced ionic equation. So in the homework, I've got some of these types of questions. There's a lot more theory in these couple of chapters. So please do at least read through the theory. If you want, you can kind of go straight through just reading the answer key and getting a better understanding of the chapter. Okay, without having to worry about doing the actual problems, because for the most part, the questions that I'm going to be giving you for this unit and for eventually an assignment that we'll be doing, I don't know, maybe next class or the class after. is going to focus more on calculations. Okay, so we are going to focus more on the calculations aspect. Okay, so that is it for this evening. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.